Is extinction forever? Once a species takes its last breath, is there nothing we can do to fix the problem? No solution to undo our wrongs? Humans are the main cause of extinction, and a number of examples embellish the pages of history. Yet what if we could bring back extinct animals to make up for our past actions? It may be surprising and sound more like science fiction, but today, de-extinction is possible. Hello, my name is Abbegail King, and today I'll be discussing de-extinction as a medical and environmental solution which encompasses an ethical quandary. This presentation is part of a Capstone project in Humanities 220 at Haywood Community College. Throughout the process of defining de-extinction, I will be discussing the verge of extinction, the science behind de-extinction, and environmental health, in addition to sharing both benefits and concerns related to the process. Today, there exists a great number of endangered animals. These animals, just like many before them, are on the verge of extinction. Throughout history, we have lost a great number of individual animals for a number of different reasons, leaving many species in a critical state. Yet endangered species are not yet vanished. They are on the verge of extinction. So what does it mean to be fully extinct? When a species has a breeding pair left, able to reproduce and form a new generation, the species is extant, meaning still existing. If, however, a species exhibits no breeding pairs for a number of different reasons, the species is typically considered extinct. These creatures are officially declared extinct when their last species member dies. There have been many extinctions throughout history. These can be found within the fossil record. The fossil record is defined as a collection of fossils and remains buried in layers of sediment. These remains provide insight into past life, including extinctions. One such extinction displayed within the fossil record is that caused by the arrival and advancement of humankind. The record shows a great loss in biodiversity around the time humans began to create more advanced weapons and transition from hunting societies to agrarian societies. Many of the species lost in this extinction consisted of megafauna. These animals roamed nearly every continent and consisted of many large animals including woolly mammoths, giant ground sloths, woolly rhinos, aurochs, and saber-toothed tigers. These extinctions are thought to be caused by humans overhunting and habitat changes. Many of these animals cannot reproduce very quickly. For example, a mammoth's gestation is believed to be a long 22 months, with only one calf born at a time. If overhunting occurred, the animals could not keep numbers high due to slow reproduction. The auroch was a large bovine which roamed many continents of the world. They were an ancestor of modern cattle and a keystone species in Europe. Sadly, aurochs were extinct by the early 1600s, though their relatives still roam the earth today. Aurochs were often depicted in cave paintings with other animals, such as this one from Chauvet Cave in France. These images date back to the late Pleistocene epoch. But extinctions didn't only happen a long time ago. In fact, they continued into the 20th century. Two recent extinctions include the thylacine and the gastric brooding frog. I'll be discussing each of these species a little more in depth. The thylacine, also known as the Tasmanian tiger, was an incredible marsupial native to the island of Tasmania. In 1888, the government placed a bounty on thylacines as they were labeled a nuisance. And by 1909, at the end of the program, 2,180 bounties were given. Due to their already low numbers, in addition to the overhunting, thylacines could not survive, and they were declared extinct by 1936. Causes of extinction include habitat loss, overhunting, and introduction of foreign diseases. The gastric brooding frog is the most recent extinction I will be discussing. This species was only initially discovered in the 1970s. This frog has quite an incredible ability and can control the level of acid in its stomach. Instead of laying eggs and leaving them, gastric brooding frogs swallow them. The stomach then turns into a uterus where the eggs hatch, tadpoles grow, and eventually little frogs hop from the mother's mouth. This ability is significant to medical research, especially within gastrointestinal problems. Sadly, the gastric brooding frog was declared extinct very shortly after its discovery in the mid-1980s. Cause for extinction is thought to be pollution and habitat loss, both of which are caused by human industries. But I'm sure you're wondering, how can de-extinction even be possible? The animals are gone and there's little hope of finding them still hiding somewhere on the earth. The answer to this question lies in what the species left behind. This key proof of their existence also holds an important aspect of the de-extinction process in the form of ancient DNA. Some of this matter, which includes DNA, includes skin, such as the mammoth skin in the top image, full specimens like the thylacine pups, which are placed in alcohol, in addition to hair samples and their living relatives. When I first stated the word de-extinction, what came to mind? For many, it may be something like these images taken from the popular Jurassic Park film series. While we may not be bringing back the popular dinosaurs anytime soon, we must ask if de-extinction is really just science fiction. It may come as a surprise, but the scientific basis for de-extinction already exists. Remember Dolly the sheep from the cloning efforts in 1996? Well, this important scientific advancement may hold the key to de-extinction. Here's how it works. First, an unfertilized egg cell is removed from a donor animal, and the nucleus containing genetic makeup is also removed. Then a cell, which is not an egg cell, is taken from the animal which will be cloned. In Dolly's case, this was a mammary cell. The cells are merged with the hope that they will create an embryo and continue to divide. If they do form an embryo, it is placed within a recipient animal through embryo transfer. Eventually, a lamb is born and is genetically identical to the initial animal. But there is a catch. We cannot take egg or mammary cells from extinct animals. So how would this process even work in de-extinction? Scientists would start with egg cells from a living relative. They would remove the nuclei and would implant the ancient nuclei from the extinct animal. The catch is that ancient DNA is highly fragmented, so it must first be reassembled. While there is a much greater chance of failure with this process, the slim hope of success may be what allows the process to continue being conducted. According to paleontologist Michael Archer, in 2013, scientists successfully grew a living primitive gastric brooding frog embryo. Though it died shortly after, this allowed for more cells to be produced, which could be used in further experiments. Cloning is not the only form of de-extinction. Another includes backbreeding. This process uses living relatives of the extinct animal with the hope of gaining a creature which will look and behave like its ancestor. The auric is one species which is undergoing this process. Scientists use Spanish breeds such as the Spanish fighting bull, European breeds like the hardy carry cow, and certain zebra breeds to select traits and breed for an animal like the auric. The end result will not be a genetic member of the auric species, though it will be able to function in the ecosystem like the keystone bovines. The last form of de-extinction is that of splicing or insertion. This process involves the use of the full genome of an extinct animal, such as the passenger pigeon, and a distant living relative, like the chicken. Passenger pigeon DNA is spliced into both hen and the rooster, and this causes their reproductive system to pass on passenger pigeon DNA into the eggs and sperm. This means that the hen lays passenger pigeon eggs, which can then be incubated to replenish passenger pigeons. Why should we go through this complex process, though? Why do we even need these creatures? It's not only that we need them, but that we have a moral obligation to de-extinct, as we were the reason for their initial demise. In the words of Stuart Brand, some species which we killed off totally, we could consider bringing back to a world that misses them. There also exist benefits to de-extinction aside from the satisfaction of our wrong. Extinct species may be able to restore habitats and ecosystems. Some species, like the auric, were a keystone species with a role similar to the American bison. Bringing them back could help with the restoration process of European grasslands. We have also lost a great amount of biodiversity and could restore biodiversity partially through de-extinction. Lastly, species such as the gastric brooding frog could hold incredible medical information to assist other animals and humans alike. Just as there are benefits of de-extinction, there are also risks. Today, endangered animals face pollution, climate change, and poaching, all of which could counteract de-extinction efforts. In addition, we must consider a moral obligation for the well-being of de-extinct creatures. Some argue that the scientific basis for de-extinction is ethically wrong. These are both important concerns in the consideration of de-extinction. Can Earth support de-extinct creatures naturally, or would they forever be confined to captivity on the verge of a second extinction? The answer to this question is unknown. We have the tools to de-extinct, but using them and considering them with utmost moral and ethical responsibility is perhaps the most controversial aspect of de-extinction. In summary, I've discussed human-caused extinctions, the science behind de-extinction, and some environmental health benefits and concerns associated with the process. My references for this presentation. Thank you for listening.